last day of our military review. Like yesterday was already fun. All right, so multilayer perceptrons, and what's happening here is basically we have neurons organized in several layers, and this is like not basically reducing the amount of layers that you can have, but what is going on here is basically you have an input layer. The duty of this input layer is nothing but getting inputs for the different dimensions and then distributing that across. So this one neuron basically just is like a linear function neuron that distributes the information to all of the other neurons that are in the next layer. So these are fully connected neural layers, and then this layer is connected to the next layer, and you can see there are no connections between layers, right? And there are no connections from this layer backwards. Okay, so there are also no connections between neurons themselves, so there's no recurrency. Like this is a feed-forward neural network, basically takes information that comes in here and produces the output at the end. Okay. And first, we're going to talk about how these neural networks process information once they are already trained, and then we're going to talk about how we train them. Okay. So first, this neuron is already trained. The important things that are to note here, basically n input dimensions, L output dimensions. We have notations WKI, which are the connections between layer 0 and layer 1, KI, and then layer 1 to output layer 2, which is WJIJ, neuron I, neuron J, okay? And the hidden layer has a transfer function of like a sigmoidal function. In this case, tangens hyperbolicus, could be linear, like this one, could be anything else. But also this just visualizes that they can have different functions, okay? The output layer in this case, and this is also the example that we're gonna derive the update functions for, is gonna have a linear output layer and a sigmoidal hidden layer, okay? All right, so each circle denotes a perceptron with different transfer functions. Multilayer perceptrons are very powerful. They are universal approximators, and for understanding these neural networks, we need to understand two processes. First, the retrieval process, which is basically the application phase where the neural network produces an output for a given input, and the training phase where we update our weights, and we only update WKIs and WIJs. So all that is here and here, we update nothing else. Okay, so we don't update the transfer functions, or we don't update the number of neurons, we don't update the number of connections. If we want to switch off a connection, well then we would learn that one of those would be 0. Okay, that would be the way to remove a connection, right? All right, but that's generally not really happening. Okay. Yeah, so in the next one, in the next slide, we're going to use superscript. So WKI already should tell you that this is the weights from here, but we're also going to have like a superscript which says like 1 in brackets. It just says, okay, this is from here, and here we'll have a 2, so you know that this is the connections that are in the second layer. Okay, so that's just as a note. All right, for retrieval. So what we need to do for retrieval, we talked about this before. Well, at each step or at each neuron, we kind of have to compute the dot product between input and weights and apply the transfer function, right? So here we just produce x's, and here we sum up over these guys and produce sigmoidal output. And then here we sum up over these guys and produce the linear output, okay? So always dot product between the weights and the inputs, and then apply the transfer function. Okay, so for these guys, because these are boring, we start here. So basically, what will be the membrane potential of this neuron is A, and it's the weighted sum between all the connections that this guy has to the others, and the inputs that are coming out from here. Okay? And we can denote those as xk because these neurons don't do anything. Okay? And then we apply the transfer function. In this case, it's the tangent hyperbolicus, and we decide what value to output based off of that A. Okay? And so now, what comes out here is this y of 1 or f1 of AI, and basically what the next neuron outputs is yj2, or the transfer applied onto their membrane potential, which is nothing but the linear function. So it's just the, because this is linear here, it's just the weighted sum between the weights that are here. So for this neuron, it's this, 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 and this, multiplied by whatever these four output, okay? So that's basically what these outputs here will be like, okay? Does that make sense? Yeah, so again, each neuron does two steps when computing the output of the, itself, and it's the weighted sum, and apply the transfer function. And if those are always linear, for example, the transfer function would be non-existent. Okay. So this is how we approximate functions, for example, like the y could be used to approximate any function. But if we want to do classification, well, how do we make the decision which neuron won? Well, we need to look at all the outputs here from 1 to L and basically choose the one that has the maximum value. So we just choose the argmax to make a classification. Okay? All right. So let's look at learning or training in these multilayer perceptrons. So first of all, we had discussed that before. So what we need to identify is an error, or like a cost criterion, a criterion function. We need to identify how far off are we, and we want to move in the negative gradient, or the down the gradient, and we want to minimize that error function. Okay. Where do we observe error? Well, we only observe errors here because we'll have like a target signal here that tells us how bad these outputs are. Okay, we don't have anything here, but we do want to update both these weights as well as these weights. Okay, so the problem will be that we only observe errors here, but not here, but we still want to update all the connections. And what we basically have to do is we have to send the error back through the network, and that's called error back propagation. Okay, and we're going to have a slide of that. So anyways, first define our error function. In this case, again, Euclidean distance between the target and the output of the network. And what we need to do is we need to do the partial derivatives for each weight separately. Okay? And so, and in this case, the error function is also defined over an entire set of samples. So we have a sum over all samples in our training set. Here we're going to talk about this in a little bit. But basically what we have to do first is do the partial derivatives for all of these weights here. Okay? And that looks like the following thing. So the new weight is equal to the old weight minus learning rate partial derivative up here, and basically that is defined as the following. So where basically, so we have this function here. So the output is dependent, or like the error is dependent again on the output times this delta, and the delta is nothing but the output of and this is the output of this neuron here, actually, because that's our x that comes into this neuron, and so it's the output of what we have minus what we want to have, and then we apply the transfer function on our what is it? And this is with a differentiation here for the membrane potential of this guy, but it's linear, so it would just be a constant here. Okay, and so that's how we calculate the updates for these weights. All right, and basically now what we have to do is we have to remember this error and send that back through the network, and have to and now we have to update those. So what we need to do is basically apply chain rule. So to get at these weights here, we need to first derive for the outputs of these neurons, and then we have to derive the output with the weight. Basically this looks as follows, where now the delta from the previous layer gets fed into the delta of the error of the current layer, weighted by the amount of error that we have, weighted by the connection weight that we have. So that means if this guy here makes a big error, right, but it's very minimally connected to this one, that weight here would ensure that this one doesn't get updated too much, okay, because it was not responsible for that big error. The big error came from somewhere else. Okay, so you basically compute the error here, and then you weight the error with the connection weight. So if this is a strong connection, it gets strongly punished. If it's a weak connection, it gets weakly punished. And then you know what this update will be. And then in this case now, the update is dependent on the input and the error that this network does. So what is important here is that you sum up over all of them. So if this neuron doesn't make a mistake, we weight it for this one through that value, but we also sum up what this neuron makes as a mistake, okay? So we sum up over all the L neurons, which are these guys, the output guys, okay? All right. An interesting fact here, because so we have these sums here, which make it a little bit more complicated, because it's not just an update every single time step, but it's an update after you've presented many samples. So that's called a batch learning rule, which basically looks at a batch of m samples before it makes an update, which is a little bit different from an online method that updates after presenting every single sample. And to change that into an online method would just be to remove the sum there, and then just have all the mu's gone as well, right? Right, so that's kind of basically what's happening. So these additional so-called batch mode learning rules, and for incremental learning, we just remove the summation over mu. So this is the error back propagation method, and this just sums it up again, what's happening. So the error is computed at the output of the neural network as a distance between the target signal and the output of the network, and the error is fed back through the hidden layer. For each hidden neuron, the error is computed, and then basically the final error is then used to update the weights between input and hidden layer. So first we compute the error here. We understand, like we learn how to update those. We don't update them yet, but we compute a weighted sum for each of those hidden neurons based off the error that these guys made, and then we use that to update those connections. Okay. All right. So there are. I think we can talk about this in a second, but so there are like a whole kind of bunch of problems associated with this. These are just 4 examples of that. So the first example is one that comes with the gradient descent method, is you're not guaranteed to find the global minimum. It's unlikely that you actually find it. Often you'll just find a local minimum. That's how it is. We talked about methods that could, for example, alleviate that by multiple runs or something like that, okay? Another thing that could happen is that if you end up on a flat plateau of the error function, which basically gives you only a minimal, a small gradient, and if you then have a very small learning rate, the update will be very tiny, and so you're only moving very, very slowly across that flat plateau, and it might take a long time to find this global minimum, okay? That's one other issue. Another issue is in this C case where you have a oscillation happening where basically your update or your learning rule might be too large, it might be too large, and you basically just oscillate between 2 potential. So you oscillate between these values, and you jump over an actual minimum all the time. And then the last one is basically if again your learning rate is too large, you might actually jump over the global optimum and just find a local optimum because of that. Okay, so these are all like possible issues with that. Just so you know, like there are many different learning rules or possible alternatives to learning rules that alleviate some of these problems. So for example, to alleviate this problem or even maybe this problem, there is, for example, one method that looks at the gradient itself. So you check the gradient from the previous time step, you look at the sign, like is it positive or negative gradient, and if that has changed from the previous one to this one, then you go back, you just reverse the learning update that you just did, and then you walk half the way. Okay, so then you basically try to find or fine-tune at each time step where you want to end up in. Okay, so that would, for example, what would happen is you are here, you update to here. Now you see the gradient has changed. Well, what you do is you reverse that step and you only walk halfway, you end up here. Okay? So that would be a more optimal solution there. Alright, another one is momentum term learning that would alleviate this problem here. This works similarly as before. If the gradient direction doesn't change, then you just increase your learning rate. Increase, 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 increase. So you speed up over a flat plateau, and if the gradient changes, well, then you reverse again and you go slower again. Okay, so that's kind of like some possible solutions there. All right. As another kind of interesting task or topic, and this will become more important for deeper architectures, but we'll talk about that in a second, is that there are not just feed-forward neural network, but also recurrent neural networks that basically can utilize information over time. They can learn dependencies between sequences of inputs. They have a memory. They can process information that is sequential, so they're more likely to help you with problems that have dynamic changes or require you to understand what's going on in a sequence. Okay? But the cool thing is that we can learn those recurrent neural networks in a very similar way as we can learn these feed-forward neural networks. And I would like to show a couple of examples there. Okay, so one example, and you'll have that example in your slides as well, is this neural network, which basically gets inputs from here, produces outputs here, and then it has connections to itself. Each neuron has connections to itself, but then also these neurons have connections to each other. Okay? So if we wanted to do error backpropagation, it would be really hard to do this in a recurrent neural network because we don't really know at what time we are aware and what's going on really. But there's a cool trick for that, which basically allows you to do the same thing as we just did with error backpropagation through these networks, and it's called error backpropagation through time. So we kind of take this network that is recurrent and unfold it through time and duplicate the neurons basically multiple times, as many time steps as we want, and we create a deep neural network through time. So this looks like this. So we have neuron 1 and neuron 2 here at time step 0, so it gets an X as input, produces an output. Probably in the first iteration it doesn't have an output, so it wouldn't produce anything right now. But then this neuron has a connection to itself, right? So that means through one time step there will be a connection to itself, and then it has a connection to the other one. So through one time step it will have a connection to the next one, okay, which is a copy of this one. And then this one has a connection to itself too, and this one has a connection to the other one too, okay? So now is time step, so this is T0, this is T1, you have a new X, and you have a new output, and then you do the same thing again, and then you do that how many times you want, okay? And then now you have, at one time step, you stop and you say, okay, now we're done, and then you backpropagate the error through this, okay? So, and the cool thing is, here are a couple of interesting points here. Well, you don't have to unfold this network into infinity because multiple reasons, as you might recall from the slides that we had here. Yes, so here what you have is you multiply in this eta there, and you multiply that also here, and so at the previous one you have that here too, and so basically you would apply the same learning rate multiple times, and you basically would have no update to send back towards the neurons at the very beginning if you went way too far. So that the gradient vanishes basically. it goes away. Or if you didn't have the right set of parameters, it explodes and you would have to deal with that as well. So that's problematic sometimes. But anyways, so this is a method to alleviate the backpropagation through time, and you can apply backpropagation in recurrent neural networks that way. But it has its own set of problems, which basically, while this approach allows you to go like 5, 6 time steps, it will never allow you to go 100 or 200 time steps. So you can't learn these long-term dependencies. And there were like a famous new neural network that came out in 1997 that allows you to do that. And back in 1997 it was completely useless because the computational power wasn't there. But now everybody uses it for like speech recognition and whatnot. Okay, a couple of other things that I would like to talk about are the following. So, just so you understand a couple of things about the choice of transfer functions that we need to make. So, why are we not using the Heaviside function like this in this case, or here? Why are we not doing that?
Because if we have multiple classes, they will just it will just register the largest component of the input, right? Well, okay, what I'm trying to say is, because there's because it only takes, it's discriminatory after threshold.
Yeah, well, it only produces an output after like it
Threshold.
reaches the threshold, right? So it produces either zeros or ones.
Or ones.
Right?
Right.
Okay, but that's not really prohibiting me to learn classes, right? Like if I had that here, one of them would produce.
Imagine that there's an input that says 05050605 for something that is coming in. Then this discriminatory will just say it's 0.
Right. Exactly. So it's definitely less powerful, but it has it still can be used, I think.
But the one that is, of course, but the one that is 05 is in some specific cases actually a very important input.
Yeah. Okay.
That this one will kind of render out.
Right. Okay. That's a good point. Also, this function has a discontinuity here, right? Like it's
At the
you
threshold.
can't derive it at the threshold, but we need to derive it to make these to use because we have to apply the chain rule and we have to apply the derivative to our transfer functions. So that's the problem, right? Like it can't be derived at this location here, which is at the threshold. But here's the trick, that's not the reason why we're not using them. Why are we not using them? They have another problem. As you said, like they produce zeros and ones, right?
Mm-hmm.
So when we're not at the threshold, we're here or we are here. But we still have to take the derivative. What's the derivative of this or this?
0.
It's 0. So we would always
Get zeros.
eliminate everything. So they have 0 use for learning. That's why we're not using threshold functions in these multilayer perceptrons. Okay? But we can use them in perceptrons. But we cannot use them here. Okay? So that's quite important. So never use them. I don't think even like scikit-learn would allow you to. Yeah.
What is the A value in the...
Oh, that's the weighted sum between the whatever the input is and the weights.
Okay.
Yeah, it's a membrane potential, so to say. I think we have it here. Yeah.
Yeah, and there is a sidekick on Multilayer Perceptron.
Right, but it wouldn't have
No, because, no,
heavyset functions.
exactly, definitely.
It probably allows you to do sigmoidal functions and tangle supermolecules, and then it would allow you to do linear functions and so on, but not anything else.
Okay.
But there is the rectified linear units that I mentioned that basically are 0 and then they become linear. These are used so that most of the time the neurons aren't doing anything, but these are only used when you have like millions of neurons, so that a few do something, but most of them don't, so that you actually speed up your calculations, your training and stuff like that. So that's that they are used in that case. All right. So before we finish for today, I would like to show a little bit about. So I'm gonna upload this as a homework. This is gonna be. I think maybe we're gonna give you a couple of days more, but because like I'm not gonna look at it on the weekend, and I think Li-Xing will neither. But basically, and I'm not sure if this is. I think we'll probably change that to 10% less or something like that, 20% less. This is a bit. So Li-Xing made this, and as you know, fellow students are often a little bit more strict than.
That's the digit set, right?
Yeah, it's a digit data set, and basically what the data set looks like, it has a bunch of these 8x8 images that are coded with 0 through 16 values for grayscale values. So it's a very simplified MNIST digit data set. So you have like 8x8. This is a 1. This is probably a 7. What we would like you guys to do are the following things. This is basically just a little bit of like getting used to scikit-learn or Python. Just calculate a couple of statistics. You don't have to stick to mean and standard deviation, but you can, I don't know, try some fun stuff. This is only giving you 1 point, so that like if you don't even want to bother with that, whatever. But this is just like try out a couple of statistics, statistical functions on in Python. Then we'd like to see that you're able to visualize something, do some box plots, and this is really just because we'll need that for the course project. Okay, so just make sure that you try to understand how to make these plots. And here we have prime numbers, and the newest and coolest findings of math. 1 is not a prime number anymore, yes, and then we would like to do a couple of experiments. So there's experiment A and there's an experiment B down here. But what we want you guys to do is to split up your classification problem into a binary problem, a prime number versus no prime number, so that the neural network learns something interesting. So it's like either 2 outputs or, and I think we're going to use SVM, so it will have like a binary problem, so not a multi-class problem. If you are interested in doing like a 10-way classification, you can do that as well. If you want to submit that, I'm not going to hold you back on that. But basically what we want to do is, and this I think is the standard setup for SVM, so you just use this SVC classifier in scikit-learn, and we do 5-fold splitting. Try to do that manually first, and then you can also try it with the cross validation functions. The stratified method that Li-Xing mentioned in the tutorial, and then we would like you to we'd like to see that there's like a hold out 1-fold for testing, and yeah, just execute or try to like discuss what you're executing here. Then we'd like you to try to validate for a gamma value, and you can use a log space evaluation here. So you you evaluate 0, 0, 1, and you evaluate 0, 0.1, 1, 10, 100. Okay, so just basically try a few of those parameters. Then we'd like to see that you can talk about this a little bit. Talk about metrics like accuracy, confusion matrix, F1 score. You can plot the results if you want to, like maybe plot the confusion matrix or something else. And then the second experiment, you should try to use grid search and try to find like 3 good parameters, or like a couple of good parameters for each classifier. And here we'd like you to compare SVMs with some other classifiers. You can use, I don't know, like a linear discriminant, or you can use whatever is available, like a neural network if you want to. Yeah, it's up to you what you use. So this is the main part. That's just a little bit of like exercises. Okay. All right. I'll post that from the bus, which I will take in a little bit, and you will have time, I think, until like Sunday midnight or something like that. Okay. Then I also have another homework, so to say, and I hope that, well, let's change this a bit. Is it choose things? So what we would like to see is that, first of all, I hope that everybody either has decided to form a group or do the course project by themselves. But we would like to just have an initial kind of outline of what you're interested in, what data set you want to tackle. Maybe you like try to find state-of-the-art algorithms that try a similar problem. So this should kind of motivate you to first identify a problem that you are interested in, identify a data set that you're interested in, try to get like a feel for how do I search for a certain problem. I have a certain problem, want to solve this problem. How do I search the internet for like machine learning approaches, to get ideas and so on. And then I would like to see that you know how to talk about like what machine learning algorithms you think you would want to choose, and you don't have to bother about this today, like you have 3 weeks, but maybe you want to already say, okay, I definitely want to do neural networks, but in the next couple of days and weeks we're going to talk about more and more machine learning algorithms, and so that you like really have a good set of algorithms that you can choose from, so you're not like left alone on this. So this is why it's also for 3 weeks out. And what I would like to see is also a discussion of like what metrics you want to use to evaluate this. So for example, maybe your data set is very skewed, so you don't just want to use accuracy, but you want to use F1 metrics or F1 scores, or you want to have like a confusion matrix because you want to actually identify what errors the network makes, because they would be interesting to you to solve the problem and so on. So just think about this a little bit. What I would also appreciate is kind of like maybe also some ideas about how you would like to conduct your experiments, like what is going to be your training set, what's going to be your validation set, what's going to be the test set. So if you, for example, choose a Kaggle challenge, you don't have to bother with that because then you can say, well, I have my training set, I'll split out the validation set, and then they will do the test set. So you're not in danger of making a mistake there. But if you choose your own data set, I would like to definitely see how you make sure that you're not overfitting, and how you actually evaluate how well you're going to be able to generalize across new and unseen data. Okay? And we're going to formulate a document for this as well that I hope I'll upload, I don't know, maybe tonight or tomorrow, so that makes it more clear what we're expecting, how these 2 to 3 pages will look like, and so you're not in the dark about this. But it's just as an early warning that this will come up, and we'll have to move forward with the course project so that everybody is ready for submitting it at the end of the semester. All right?
Are the generative networks, the new ones that you showed us, are they an option to use?
If you want to.
I would love to.
Yeah.
I have some, the Pixel CNN, and I have some of those,
Yeah.
and they seem to be very interesting. So I don't know how good I'm
Sure.
running, but I've got some CD. But I would really love to use it because they seem to be like they're super fun now.
If you want to use that, then you can definitely do that. That's not a problem.
So do I have to come up with the slight change in the algorithm for let's say Pixel CNN? Because I won't be able to. But I don't have to use it. I won't be able to do it.
Yeah.
To make a new algorithm.
No, you don't have to.
So sorry.
I mean,
It will take me like several months to be able to do it.
but what I would like to see then is like a discussion about why you chose this approach.
I want to generate floor plans because that's a very interesting and super easy black and white image. I have to figure out how to get the data set because we don't have them.
Yeah.
I found some websites that have the ugliest floor plans ever, but if I can do some, just grab it from the web, from there, if I can do that, then that could be my training for generating new ones. Of course, small and crazy, but because they're black and white, I think they might be easier.
That'd be interesting.
And as you can notice that in psychic.
Yeah, I'm thinking about that already.
But anyways, we can start. I have other ideas.
Okay. All right. See you next week.
And then I could just do an in from that,
It's just I was having crazy.
And that's what you do.
This is just so with these CNNs, they're not anything. So I have to really change the algorithm till the end of the semester. Maybe if I take it a year, I might be able to figure it out. But I'm super slow.
I really
It's really not something that
I really expected this to work
robotics is fun.
for you.